But when we talk about something which is anisotropic, that means it will have different behaviors in different direction. In that terms, if you want to represent that same quantity mathematically, we have to use tensors. Okay? So something like moment of inertia, okay, conductivity, or maybe the permittivity and all these are actually vectors, but if only in isotropic medium. If an isotropic medium, we consider it as tensors. Okay, just a sec. Okay, so if we just consider a vector, these are all the bases I, j and k, and then we have got the coefficient of these basis vectors. So depending on how many basis vectors are there, okay, we can actually know in what kind of dimensions we are in. So if we just consider a normal vector, we have the power as 1, because with each constant there is only one basis vector associated, so we say it's a three-dimensional space and it represents a vector. On the other hand, it doesn't have any basis vector associated with it, it's simply a scalar, and tensor will be actually having a order of greater than 1. So in a way, a vector and a scalar can also be represented in terms of tensors. Scalars are zero order tensors, vectors are first order tensors, and above that everything is a tensor more specifically. Okay. So we see that there are four kinds of tensors: covariant tensors, contravariant tensor, mixed tensor, and invariant tensors. Okay. So what we do usually is we transform from one set of tensors to another tensor, in terms of coordinates. So if you're going from an S prime frame to an S frame, this is our transformation equation. And if we just want to change it, that means we want to go from S to S prime frame, we are going to do a transformation. So in a way, if I write down this as a bar I and multiply it with del x a divided by del x bar I, this del x bar I is at the denominator and this is at the numerator. So in a way we can say that we are doing an inverse transformation. So if we do these kind of inverse transformation, okay, based on which we can go from one system to another, we basically term them as contravariant. So if you want to know the difference between contravariant and invariant, covariant, right? In contravariant, okay, in a way I can just write it down here. It's is nothing but inverse. We are using inverse transformation, okay? So go from one system to another. But if you consider a covariant transformation, we are going for a direct one. Okay, we do have a direct change in transformation vectors. Okay, so this is inverse. Okay, and this is the direct transformation. So that is the basic difference between contravariant and covariant tensors. Okay, and today we are just going to look into the mixed tensors. And if you look into this, if you represent it at the denominator, we call it as covariant. If we represent in the numerator, we just call it as contravariant. So this specifically cannot be said that that's a difference. That's how you represent a contravariant and covariant tensors. The difference is, one is with inverse transformation, that we get the relation between the two system of coordinates, and in the other one we have got it a direct transformation. So let's just check some examples of mixed transformation. Okay, mixed tensors rather. So if you look into mixed tensors, okay, it will be basically a combination of contravariant and covariant tensors. So the topic is mixed tensor. So there are different content or different elements, okay, different constants which will behave in different ways. Some will actually have the property of both contravariant and covariant tensors, so that's why we should also check into this. So in the mixed transformation or tensors, the transformation equation is like this. So if you consider a mixed tensor, the order will there will always be a second order possible. Okay, there is always a second order because you have got a combination of both. If it's only one, it is either contravariant or covariant tensor. Okay, so this is del xp. So or maybe I can just write it at the numerator. Let me write down the contravariant tensors first. So del xp, this is a contravariant tensor, and then I will mix it with a covariant tensor. So in a covariant tensor it is xq. Okay, covariant tensor, we have got the representation of the basis vector at the denominator. Okay, so we have got this is the covariant tensor, where we are basically having the representation of the the basis vector at the numerator. In contravariant we have it at the denominator, and as I said the other day, x to the power p, x to the power q will remain. It doesn't it is a way to represent it. Okay, it's a way to differentiate it in that order, but when we want to represent the tensor, we actually write it down with the tensor quantity, the constant that we are considering, a p q. So it is basically a mix. It's not a to the power pq or a sub base of pq. It's a superscript of p and subscript of q. Okay, so that's a mixed tensor. So it is basically a mixed tensor of second order. Okay, that's it. And we can actually have a third order also. In third order, in general, you can have two basis vector as contra and one as co, or two as covariant and one as contravariant. Okay, it totally depends on what we need. But here if I represent this, there are two contravariant tensors. So let's just represent these things, del xp, and then it will be del x bar j divided by del xq into del xr divided by del xk ijk, right? And then this side it would be, I can represent it as pqr. We can represent it by anything else also, doesn't matter. Okay, abc also you can directly write it, not a problem. So this is my third order. So if we just go back to our previous lecture, we can check. Okay, third order. Okay, this one I have not written the third order, this is the second order. So you can see this, right? So this is the second order covariant tensor. If I go from this system to this system, I have to do a direct transformation. That means I have to take this del xi bar divided by del xp, okay, and then do the transformation. On the other hand, if you just look into third order, I've written this one, I've written third order. Okay, let's just have a look into the second order. So this is our second order contravariant tensor. So this one I will write first. So here I have this one I've written, this is there, a to the power pq is there, and then I have taken the covariant tensor. That means you have the subscript, not the superscript, and we have written this. So I have written this. Okay, so that's how you represent the contravariant and the covariant tensors. Okay, and this is the mixed tensor that we are talking about. Okay, so there is a very important thing, how do we consider the order. So if I just represent this as I, j and k, how many basis vectors are associated, based on that we can say what is the order. Okay, so this one we take, this is order 3. Okay, so we, based on this, we can also determine what is the rank. There is a very important thing to understand, that sometimes we can actually have a tensor something like this, I, j, k, and then at the base also it's k. Okay, and maybe I can just write down I also. So this k that we have, it is getting repeated here. This is a k, this is also a k. Okay, so since k is getting repeated, when we write down the order, we really don't consider it, because if you write it down that way, that here it will more or less cancel out. Okay, so that's the reason that this k term, which is a basis vector, doesn't have any effect on the resultant of the tensor. Okay, so this k, I can write down, this k is repeated, or we call them as dummy indices. Dummy, okay, dummy, dummy indices. So when we consider the order for, and if we have a dummy indices, we ignore the dummy indices, so both these k's won't be considered, so the order will be still 3. Order is 3. So sometimes you get a question, even if you go for those entrance exams and all, okay, they ask you that what is the order of this tensor. They will just give you a tensor and they will repeat something. You have to know this property. Based on that, you can directly say it. Okay. So maybe I can represent few tensors here. Let's say I will write down a I j. This is something which you have already checked. So let's just write this down. So this is a second order contravariant tensor. Contravariant. Okay, Aij, and then if I write down it as something like Aj, okay, and then let's say I write down I here. Okay, this is also second order. Mixed tensors are always second order. Second order mixed. This is mixed, right? And then I can write down this as Aij. I'm just clarifying everything. We have already done it. Just listing it down so that all of us can recall this. Second order covariant. Okay, so you'll be given a tensor. You have to identify what kind of tensor it is. Okay, and if you know how it is represented, you can easily say that whether it is contravariant, whether it is covariant, or a mixed tensor. Okay, the next kind of tensor that we have actually checked is an invariant tensor. Okay, the next is invariant. So you know, in a way we already know the meaning of invariant. There is no variation if we go from one system to another. Okay, so invariant tensor, the fourth kind. So your syllabus does mention about invariant and covariant. Okay, but I'd like to just mention these all four. Okay, all four are very important. So there can be different ways of representing it. Let's say I have got this as s and then function of x1, x2, x cube and so on. Okay, and any of these terms may be xi, and then we have got another system s prime, and this will be again, if we talk about this prime frame, we usually represent it as bar cubed, and then any of the terms may be xi bar. So we have this, and then there will be tensors on both sides, and let's say we represent a tensor by phi. You can represent it by anything else also, and it may be a function of I will be same as the tensor which is again phi bar because it's in the s prime frame, and this is a function of, let's say, okay, so this is a function of xi bar. Okay, this is a function of xi bar. Okay, sorry, xi bar. So both of them are equal. Okay, there is no variation whether you go in this system or in the other system, so that's why they are called invariant. No variation because they are invariant. Okay, so this is how we actually represent another tensor. So maybe I can write it down here, right? Since they are equal, hence no effect of frames of reference. So no effect of frames of reference when we actually are considering the tensors, whether in one frame or the other frame, and that's why they are called the invariant tensors. So it's the simplest one. Okay, there is no such thing as transformation because you don't need have any kind of changes here, so there is no transformation equation. Okay, so these are the four kinds of tensors that we have in general, and I hope you also got the difference. When we talk about contravariant, we are talking about inverse transformations. Okay, to go from one system to another. When we talk about covariant, we're talking about direct transformation going from one system to another. In a mixed, it's a mix of contravariant and covariant. And invariant, the tensors remains the same whether you consider this frame of reference or the prime frame of reference. Okay, so in a way it's not complicated, but you have to just study it in sequence so that you're not confused. Okay, the next thing is rank of tensor. Okay, let's just check. We have already mentioned it superficially, but let me just take this topic specifically and talk about rank of tensor. So if you look into the rank of tensor, I think the best way to understand this is take up some examples and write down the rank. That's it. So if I write down A, let's say this is P, this is Q, this is R, this is S, this is T. So see, the rank higher means it's going to be your more equations more complicated. There are different ways of representing that. So the rank is 5. So fifth rank. This is a fifth rank tensor. Okay, because there are 5 basis vectors here, P, Q, R, S and T. Okay, and suppose I will take an example here as A, P, Q, R, and let's say S and then R. So if we check here, this R, okay, it's repeated, right? R is repeated. If you just check the repetitions here, and without doing any kind of calculation, you can straight away say this is a third rank. So whatever is repeated is not considered. We are not considering R, we are just considering P, Q and S to determine its rank. Okay, so the repeated one is not counted. So this one you have to remember, that's very important. Okay, and there are certain properties of tensors, okay, which you are going to look into, but let's just look into certain terms here. Okay, let's just have a look into certain terms. Okay, so this is something which is basic. We already know about these terms, but we're just going to look into it from a tensor point of view. One is symmetric tensor. What are basically symmetric tensors? So if we say symmetric tensors, just give you one example here. If I write it down as A, P, Q, R, S and T is equal to A, P, R, Q, S and T. So I hope you got what I did there. You have a Q and an R, and you are exchanging their position to R and Q, and you know already how to represent them. Okay, if you just represent it in this way, you will see that there is no change. The tensor more or less remains the same. Okay, if that happens, it's basically called a symmetric tensor. On the other hand, if it changes the sign, it plus becomes minus and so on, it will basically be called as an anti-symmetric tensor. Okay, so I think we should write down that also. So if there is symmetric tensor, there should be something which is called anti-symmetric. So in anti-symmetric tensor, what happens is A, P, Q, R, S and T is equal to minus A, P, R, Q. It's not always mandatory that it will be symmetric. It can be anti-symmetric also. So order is important, because in vectors we know order is important. Then even in tensor it should be important. Q and R. This is R and Q. Okay, and then there is a negative sign. So this is an example of anti-symmetric tensor. Okay, so these are certain things that we should know. Okay, important. Apart from that, there are properties of tensors. There are a lot of properties, but just I'm going to discuss 2 or 3 important properties. This symmetric and anti-symmetric also, you can consider that one of these properties that actually comes into effect. Let's just have a look into the properties of tensors. Okay, so if you look into the properties of tensors, okay, let me just tell you the first property which is important. When you do your calculations, you'll need it. Suppose you have got a tensor something like this, I, J, K, Let's take an example of a mixed tensor, and if you add it with another tensor which is also having the same order I, j and k is equal to, you will get a third tensor c, I, j and k, and this is actually a property. Okay, so the rank will remain same even after addition. Okay, so the rank remains same. Important property. Let's just try to prove it. Let's just try to do in some calculations here which we already seen. A, P, Q, R bar. So let's just represent these. So del x bar P, and then del x bar Q into, we can represent R, so del x bar R. Okay, so when you write it down, probably you should do it this way so that it becomes easy. And with P we have got I, so del x I, this is del x j, and this is del x k. Okay, this way it's easy, and then I can simply write it down as A, I, j and k. So this can be 1. Okay, and then in a similar way we have to get another tensors written, so I can write it down as this B, PQR bar. So I write it down, this also same thing, del x bar P, del x bar Q, right, and then this is del x bar R. So this is del xk, this is del xj, this is del xi. So I can represent it this way, and then we can actually write it down as B, I, j and k. Okay, so we need to add them up, so we can just add them up. Okay, let's see what happens after addition. So A, P, Q, R bar plus B, P, Q, R bar is equal to, okay, so what we can do is we can take certain things common. You'll see that both of them has got this tensors coefficient is common. Okay, both of them have got this del xp, del xq, del xr. Okay, I think that is r, right, not a k, sorry. Yeah, okay, this is correct. R, this is xi, xj, xk, and then we can write down this as a, I, j, k, this is different, plus b, I, j, k. So if you write it down in this way, okay, this will actually represent the same, because for the simple reason that their coefficient is the same. So this is going to represent one simple tensor. Okay, so if we want to represent it, we can just simply write it down as c bar p q r, and then we have got the bracketed term, and then this can be represented as c, I, j and k. So even if we add, the the system does not change. Del x terms will more or less remain the same. Okay, so in this way we can say that this, if we add up, we are going to get a mixed tensor which is also having the same order, because if we check here, the order more or less remains the same. So here the order remains same. Individually A, P, Q, R has same order, B, Q, P, Q, R has same order, adding up also makes the order same. So you can just represent it with a single tensor SC. So in a similar way, okay, uh, similarly if we just take the subtraction minus B, I, J, K, it will all represent how you represent it. Okay, C I J K. So if you take subtraction or addition, more or less the order is going to remain the same. So that is very important. Okay. So this is something which is there, and we are actually taking the addition of that. There is something which is also called the outer product. So there is one more property that we should check. Number 2, outer product. So what happens here is, if we just consider these tensors, okay, maybe like this: A I J K and B L M, and then someone asks you that what is the order of this. If we multiply these two tensors, I J K L M, nothing is getting repeated here. We are doing a product of both these tensors, so you are going to get 5 different differential terms. Okay, so that means it will basically be considered as fifth order tensor. This is a fifth order tensor. Okay, so we are going to check this. So this is basically a product of these two tensors. Let's see what we exactly mean by outer product. So what I can do is, we can actually take two tensors, let's say A P Q R bar. We are not repeating anything, so B S and T bar. Okay, and if we just want to multiply them, we can just simply write it down as, sorry, can just simply write it down as del x bar P del x bar Q. It's mixed, I is at the bottom, so I'll take del x bar R. Done for the first part, and then we have got A I J K, transforming from the S dash to the S frame. So this would be del x. You can always follow this sequence in the way I'm writing, so that it's easy to remember and don't get confused here. Xj, and this is del xk. Okay, so we have it, and then we have to write down for B. So B also we can take it as del x bar S, and we have got del x bar T. So this is del x L. I told you, with respect to I it is P, with respect to J it is Q, with respect to K it is R in the second coordinate system, with respect to S it is L, with respect to T it is M. If you want to represent it with any other also, you can still do it, but please make sure you don't repeat I, J and K, because P, Q, R are not repeated. It's S and T, so this side also it should not get repeated. Okay, that's important. So this is del X M, and then we have got it as B, and this is LM, so LM will be there. Okay, so now you see that all of these are different. There is nothing common here, so it's not that you can cancel anything with anything, doesn't make any changes. So you can just combine these two, and you can keep all these 5 terms together, and you will see that you're going to get 1 2 3 4 5. There are 5 basis vectors here: I, J, K, L, M. Okay, in the prime unprime frame. So if you have it that way, you can basically consider it to be a tensor of rank 5. So it seems to be very trivial, but then the steps are important. So if I just combine them, I can just simply write it down as C P Q S, and this is R and T is equal to, I can take all the bracketed terms, the 5 terms. Okay, the 5 terms within bracket, and then we have got A I J K B M L or L M, and then I can write it down as C. Okay, I J L, and then this is K and M. So you see, you're basically going to get a fifth rank or fifth order tensor. So this is basically something which we call as the outer product. So tensor operations are not complicated. You have to just represent the tensors in the right way and then do your calculations. But in what sequence you're writing, in what order you are writing, that is very important. And for that reason, I'd say that these calculations are important.